Hello everyone, welcome to my CRV talk on computer vision for interactive computer graphics. I'm Helge Rhodin, I'm at UBC since last fall, and I'm affiliated with the Image Lab, the Computer Vision Lab, and the KIDA cluster. And this also characterizes pretty well what I'm going to talk about in this talk and what my research is about. It's about doing computer vision for computer graphics and using a lot of ML or AI techniques. I want to start with an example from my PhD thesis that I did during my stay at the Max Planck Institute for informatics in Germany. And here we were concerned with animating virtual characters using natural body motion. So we transfer this human motion onto the virtual sheep using some machine learning techniques. Under the hood is actually a very simple linear model. I wanted to bring this up because it's a really nice example of what we can do when we reconstruct human motion. Here we are using the Kinect sensor to get the skeleton on the right, but as you might know, it has several limitations, such as energy consumption, and you cannot deploy it outdoor very easily due to its active nature. So a part of my research is about coming up with simpler sensors, easy to deploy sensors, and ideally sensors we anyways have around with us. Here we do motion capture just from a single RGB camera, a webcam, as I'm using to record this talk. You see my performance on the back. On the bottom left, you see the output overlaid with the input stream. So this is the skeleton reconstruction, and what is important to note here that it's not just a 2D detection in the image, but a full-fledged 3D reconstruction. As you can see on the left, we animate a virtual character in Unity, and you have the full 3D body pose. You can see it at the shadow. It's really in 3D, you know what is in front, what is behind. So that's what we call this full body 3D pose estimation or motion capture. And in a lot of cases, a single camera is quite a good use case, but of course we are limited to the field of view of the camera. So in another work, I've looked at different capture modalities. What we see here is what we call egocentric motion capture. You attach a camera to the head or to some head-worn device of the user, and now the question is to do motion capture from this egocentric first-person perspective. Yeah, on the right you see two of our prototypes. Of course, you could also imagine to embed that in the actual device. If you are one of the manufacturers, that should be possible. But it's really challenging to do motion capture from this perspective. On the top right, you see the input, and due to the close proximity of the camera to the user, we have to use a fisheye lens, and because of that, we get these weird deformations. We see pretty well how the upper body is visible, but we don't see the feet very well. So there are many challenges which we address with geometric reconstruction techniques as well as some machine learning. And it enables quite nice applications. I don't know if you have tried VR yourself, probably you have. You have a pretty good feeling about the environment around you, but if you look down, you don't see your own body. You might see maybe your handheld device, but you don't see a representation of your entire body. So by reconstructing the full body motion from the VR or AR device, we can immerse the real body into the virtual world and use it as a visual feedback, but also as a means for interacting with virtual objects. So you can grab something, you can push a button if we know where your real body pose is in your relation to the virtual world. This overcomes this problem of having a fixed camera and being bound to the capture volume, because now you carry the camera with you around. Way, of course, of carrying the camera with you is a personal drone which follows you. This was done during my stay at EPFL in Switzerland, and yeah, of course we had to do skiing, and here we tried to find an algorithm to find the next best view with a pretty standard approach in robotics, a quite classical problem. Here we do it for dynamics, for the dynamic target of the person, and the really interesting question is of where should you move your drone to get the best possible reconstruction of the person, and this comes with this additional uncertainty that you don't know how the person will move in the next frames. This is something we're going to present at CVPR in a few weeks. One question I was really interested in at EPFL was, well, is it really practical? Is it good enough to be deployed in practice? For that, we collaborated with professional athletes, essentially from the Swiss and Austrian ski teams. We analyzed their professionals about speed and other performance metrics using vision-based algorithms. This was work by Mirella and Roman. We are able to, for instance, analyze the speed over time. Of course, you could put gates and get the speed from point A to point B, but now doing motion capture and accurately localizing where the person is, we can not only analyze what the person is doing, but for instance also how fast the person is, and get with speed profile, see where did the athlete lose or gain speed. In a conclusion, we are really good at estimating human pose in indoor environments where we have good data sets to train on, but it's still very challenging outdoors, and we need to develop customized solutions. So at EPFL in Switzerland, we developed one for skiing. Now, me moving to Canada, we would have to develop a new technique, for instance, for ice hockey. This is a bit tedious. Each time you would have to annotate a new data set, tune your algorithm. So I'm looking, in my research, I'm looking for solutions which train much easier, which don't require so much user input to branch into a new domain. And one solution I used extensively is exploiting multi-view for training. Usually you would train your neural network to given one image to output a certain ground truth pose you obtained by either manual annotation or by some dedicated motion capture device or a combination of the two. And what we used here is simply the fact that we record the sequence with multiple cameras synchronized from different angles. And now we can come up with weaker supervision signals. We can say not only given one image produce a certain pose, but if we don't know the pose, we can still say, given two images, I predict the pose with my neural network, and what I know is that the pose needs to be the same up to the view change, so we can enforce this view consistency constraint. This is something we showed at CVPR. So you train your method on multi-view data, you have a few annotated frames, but then a lot of unlabeled frames where you simply use this multi-view constraint as the training signal, and by that you can improve results. And yeah, this was just one approach I had in this direction. I want to go into a bit more detail with another self-supervised learning approach we presented at ECCV 2018. So with self-supervised learning, the idea is that you have some auxiliary tasks. If you're doing pose estimation, it doesn't have to be something like pose consistency across views, but it can be something completely else. And you might know about a few self-supervised learning techniques already. Here we use the task of novel view synthesis for self-supervised learning. And the idea of novel view synthesis is that given one view, you want to synthesize how the scene, or in our case, how the person looks from another view. And in contrast to existing self-supervised learning techniques, which are usually reconstructing or learning 2D features, because the self-supervised tasks that are set up are something like coloring the image, so inherently a 2D task which you do in the 2D image. Here, with the novel view synthesis, we are able to extract 3D information to make the network learn. So a few more details on that. The idea here is that we use novel view synthesis as an auxiliary task to learn a 3D representation. Here's just a schematic. We start from an image, and then we have an encoder-decoder structure similar to an autoencoder, but now not decoding to the same image, but to a different view. Again, we assume we have multiple views available, so at training time, we have a supervision signal of how the person looks like from another angle. Another question is, how do you structure this encoder? How do you structure the embedding? And what kind of decoder do you use? The baseline, as I said, is already an autoencoder. Here we could learn a compact representation by learning an encoder which maps to a low-dimensional space, and then a decoder which maps away from that. Here in this schematic, always these triangles are encoders and decoders, and the vertical bars are latent representation. And the information flow is from left to right, following the arrow. And in the end, we train this method on a simple reconstruction loss. Essentially, you can compare each pixel of the output to each pixel in the target image, in this case, the input image. So now the change for novel view synthesis is that we don't try to reconstruct the original image, but you try to reconstruct this other view from the other camera. And we assume that we know the view transformation between the two. So this would be a rotation and a translation matrix from one camera to the other. Here we neglect effects due to translation and only consider rotation, because we have a tight crop around the person and we can make this assumption. And one easy way would be to give this kind of autoencoder, this encoder-decoder structure, additional information about the rotation matrix. So we give the input image, gives how much the person should be rotated, and then the network should learn how to predict the rotated output. That somewhat works, but not very well, because our training set consists of 4 cameras having 4 different views on the person. But as you can see, the method was overfitting on these 4 views, not being able to synthesize in between views. So that's why we came back to ideas from Hinton et al. On transforming autoencoders, and others have followed the same principle in the meantime. That is not giving the rotation matrix as an additional parameter to the network, but explicitly rotating some 3D space by the amount of the view change you want to do. So this is a really simple change. You start with the encoder, and instead of outputting a vector, now we output points in a 3D space. That's what's visualized with the 3 vertical bars. You can think of this as the x, y, z position of points, and in this case we map to 200 3D points. And then to model a view change of 90 degrees, then we would rotate the 3D point cloud by 90 degrees. That's what you have seen in an earlier example where we had these points flying around. And then the decoder would take the 3D points and output an image. And this is again a black box neural network. It would be probably a fully connected neural network to map this 3D space to a spatial layout, and then you have convolutional layers to decode this representation. That's what we have seen before. We can map to the 3D space, rotate the 3D space, and get a nice visual output on the right. Of course, by now, this is results from 2018. By now, we have much better generative models for generating images, so you could get a higher representation as well. But my interest here was really on reconstructing a rich latent code, a geometric latent code. So essentially, by this, we don't have the neural network learn to rotate, but we just have the network learn to map to 3D space and then map again, decode again from the 3D space after rotation. We have a couple of additional contributions here. So first of all, we are interested in modeling the person, not the background. And you might have seen that already before. We were able to remove the background. How did we achieve this? We simply give the decoder all the information we don't want to learn. We don't want the encoder to learn. So we computed the background image simply by averaging out the pixel values over time. If we have a static camera, we can easily remove the moving person. And we gave a static image always at training time to the neural network. And so it was learning to superimpose the person on the background because the background was already perfect in the reconstruction. And if you do that, you can, at test time, you can feed a new background image. It could be a white background or some arbitrary picture you may have, and the network learns to superimpose the two. Another contribution we had was that we figured out that not all the latent code should be embedded in a 3D space. Like, think about appearance, about color. There's nothing which you want to rotate in 3D space. There's no meaning for view change for color, for instance. So that's why we structured our latent space. Additionally, we split it in 2 parts. The 3D, let's call it pose part or geometric part, which goes through this rotation, and then also an appearance part, which is simply mapped through from source to target. So there we don't want to have any transformation. Now the problem is, how can you separate the two? How can you enforce the network to only store 3D information in this lower part and only appearance information in the upper part? And the way we came up is that we use a third image. So not just a pair from 2 cameras capturing the person at the same time from a different angle, but now a third view, a third image of the same person from a random time step. Because we use videos here, we simply use a random camera at a random point in time, use this image, encode it with the same encoder, and now we exchange the appearance code. So we have essentially time varying and time invariant information. And our assumption was that appearance is time invariant. It should still be the same from a previous step. But of course, pose changes throughout the video. So there should be no information, no pose information in this encoding from the other image. And that's why the network learns to take only appearance information from this additional time step t prime and all the pose information from the lower part. So by that, we enforce that no pose information is leaked into the appearance space. And that worked pretty well. So now we have a representation which we can use for editing tasks. We can take 2 embeddings and interpolate in the latent space and then decode the interpolated part. So you get a natural motion between 2 frames. And that is very much different from what you would get from image interpolation, right? In image interpolation, you would interpolate pixels. Here we really learned the space of human poses, and interpolating in it gives you gives you realistic poses from A to B. And because we have this separate space, we separate into appearance and pose, you can also do cool things of taking the pose from one person, here from the woman, and mixing it with the appearance from the guy. So we exchange the appearance space, but we keep the pose space constant. And because we have this disentangled space, we can see that we can do these editing operations. So we can independently mix appearance and pose between targets. And again, you could also do the pose information, pose interpolation on top of this. Our main goal was to actually, and here I want to come back to the initial goal, to improve pose estimation. So the idea was that we first learn this latent space, which encodes 3D pose already implicitly, and then we train an additional decoder, pose decoder, which goes not straight from the image to 3D pose as other baselines are doing, but goes from the image to latent space, and then from the latent space predicts the pose. And as you can see here, the pose estimates working on the pre-trained model work much better than the other ones. So to sum this up, this is another way of doing self-supervised representation learning. We know about a lot of techniques learning 2D representation, for instance by coloring, but this is one of the first methods using or inferring a latent representation, which is actually geometry over there, which has some 3D structure and proved to be important for doing pose estimation, or proved to be valuable pre-training step for pose estimation. Now we have been working on extending this, so this was at CVPR 2019. Here we work now with full frame images with several persons in the scene, so you first have to detect objects and then embed an encoding for each of them. And of course you can do nicer things, so now you can do novel view synthesis, not just of a single person but of multiple persons, and you could also change the order and composition of the images as you would like. This self-supervised learning was a really good example of how my daily research looks like. In the last few minutes I want to give you also some related insights of other things I'm doing. One of them is neuroscience application. This is in collaboration with Pavan Ramdia at UPFL, and I'm continuing that with the set of people here at UBC. The idea is to do motion capture for laboratory animals. How is that of use? Well, the neuroscientists, they have these complicated microscopes and genetically modified animals to be able to see neural activation. So you can shoot a video of the fly's brain or neurons and see when is the neuron active, when is it inactive. And they're trying to relate the neural activation to behavior. But until now, they had to manually annotate a lot of images to get any sense of what the fly is currently doing in relation to the neural activation. Now with automated visual motion capture, we can get the same. We get the 3D motion just by vision-based motion capture. This was here our work on DeepFly 3D, we call it, which we published at eLife. The interesting part about these neuroscience applications is not only that it's super useful for the neuroscientist itself, but there are also some key computer vision challenges behind that. And of course, the foremost one, how do we get annotated data? Every fly looks different. If we change the setup, we're going to have a different background, we have different illumination, and an algorithm trained on one domain will not generalize to the other. So one idea we had here, coming from the computer graphics background, is can we use synthetic data? And we found this fly model on a publicly available marketplace. We could buy it for $50. The problem is that the synthetic data doesn't quite look like the real data. So what we tried here is an image-to-image translation task. It's related to GANs. So we are trying to translate with kind of a cycle GAN from the synthetic domain to the real domain. But the problem we face here is that we have first of all these thin structures, the legs, which are really difficult to transfer. And also, if you think about translating from zebra to horse, it's mostly a change of texture. But here was actually a change of structure. So the body needed to be shrunk, the legs to be repositioned a little bit, and the existing image-to-image translation methods, they don't succeed on this data. So we came up with a solution which independently changes the shape of the domain from one domain to the other, as well as the appearance. And another thing I was interested in, and that's something I'm now integrating more and more into my works, is exploiting physical properties such as gravity. A very fundamental problem in computer vision is if you do monocular reconstruction, you don't really know the scale of the object. It could be a big object further away or a small object close to you. You cannot infer that from a single image unless you have some reference object of known height. And here we figured out that we can actually use gravity as a reference object. So even though we don't know any scale here in the image, we know that the person has to fall down with 9.81 meters per second squared. And this essentially gives us a reference. It's not a spatial reference, but over time, if we know the frame rate of our camera, we can use this as a scale estimate and infer back the height of the person. And yeah, you can imagine that we can use that also in other ways for self-supervised learning. In sum, I work a lot on human motion capture, on diverse techniques to ease motion capture in everyday situations. And they're really interesting computer vision problems. What I focus on is self-supervised learning, and as well as integrating domain knowledge such as geometry and gravity into the problem. Yeah, now, as I indicated, I'm at UBC. If you want to reach out to me, I put the website, email address, and my physical location on the right. I also want to thank all my collaborators, and that's quite a large crew. So during my PhD time at MPEI, and I'm still collaborating with a lot of these folks, these are the people to give credit to. At EPFL, I was also working with a broad set of people, and mostly in Pascal Fuhr's lab, and connect people from neuroscience and medicine. And now at UBC, I'm starting my own group. So here just an overview of the people who are currently in my group and who are supposed to come in summer or September. Let's see how the whole situation turns out. And yeah, thanks for your attention. I'm happy to receive any questions by mail, PM, however you find out and reach me.